In the last few sessions, we saw application of sign convention to reflection, application of sign convention to refraction. Now, these questions have been asked many times in the board examinations. So, it is worthwhile to look further into that, and in that context, today we will be looking at a new quantity called magnification applied along with the sign conventions, and then eventually take up a few problems based on magnification, sign convention and ray diagrams. Now, ray diagrams are some things that you will have to practice quite a lot, because you need to get your rules of formation of image correct, and just remembering the rules will not help you easily draw the diagram in the examination on the spot. So, it is best to practice the ray diagram a couple of times, and that will give you a very good idea as to what kind of image is formed in case of a convex mirror or a concave mirror or a convex lens or a concave lens, depending on the situation. So, what we will do now is, first of all, we will take a quick recap of different kind of images formed by concave mirror. So, let us take a look at that first. So, here is the first optical instrument. We have done this earlier, but we are going to look at the same thing from a different point of view now. Not only are we interested in where is the image formed, what is the nature of the image formed, but now we will also be looking at what is the size of the image formed, whether it is a real image or whether it is a virtual image. We start with the situation where there is a concave mirror which is of focal length f, and this is the focal point. Twice that distance is where you find the center of curvature, and there you see an object at a reasonably far off distance. I am not saying very far off, right? I am not even saying that it is approaching infinity, reasonably far off distance. So, in all these different cases of simulations that I am going to explain now, you will have to stay focused on the focal length of the mirror, which of course will remain constant. We are not going to change it now. Object distance, which is at 60. Now, I hope you also understand why we indicate a minus sign here. Note, values displayed with sign convention. And remember what I told you in the earlier session, in board exams or for that matter any competitive exams also that you are going to write later on, neither will the values be given with sign convention in the question, nor should you quote the answer with sign convention in your answer script. In all these cases, what you have to do is, you have to use sign convention to understand what the sign convention tells us. So, keeping that in mind, the minus, now you understand why there is a minus sign there. There is an image distance, of course, with a minus, and this is the height of the object, this is the height of the image, and this is the new thing that we are going to discuss more about, that is called magnification. But just by looking at it, you see the object is there and this is the image. Just by looking at it, you understand that the image is smaller, but you call it, you name this in a more technical way, you say image is diminished. So, the image is diminished, the object is facing upwards, image is facing down, so it is inverted, and you do not see any dotted lines anywhere. So, the reflected rays, they are coming to meet at this point on their own. Therefore, you say that it is a real image. So, what are the three qualities of image that we have to continuously assess the image for? One is the size of the image, either enlarged or diminished. One is the nature of the image, is it real or is it virtual? And another aspect of the image is it erect or is it inverted? So, this is a real image and it is inverted. Now, see what happens if I bring the object closer. I bring the object closer and I hope you are able to observe these things. Now, for a moment, don't worry about all these values. We will be calculating that later on. Just observe how the image is getting redrawn every time I move the object. So, I keep moving the object closer and closer, and you notice that the image is moving farther. You can clearly see that, and another thing that you observe is that the image is also becoming larger, right? But it remains inverted. It remains a real image, it remains inverted, but it is becoming larger and larger and larger. Now comes a very important point here. When the object is at center of curvature, the image is also at center of curvature. And at this point, the size of the object is same as the size of the image. Why do you see a minus sign? Because the image is inverted. You see that the object is pointing up, image is pointing down. This is how beautifully everything is interwoven into each other. Right? The mathematical aspects will tell us the physics behind it, and the physics can be understood by what the equations tell us. This is how they are closely interrelated to each other. Let us bring the object even closer. Now you see how rapidly the image is becoming larger and larger and larger, and very soon you find that the image is being formed so far away that it can't even be fit on the screen here. And this will happen in your board exam. That is why I keep telling you, practice the ray diagrams. Otherwise, in your board exam, you start with a concave mirror, you fix a focal length, you fix the center of curvature, you start drawing the rays. Then you realize that in order to join the rays, you will need 3 more additional sheets to be stuck up one behind the other, but that can't be done. Therefore, you must have a clear estimate as to what to take the object distance, where will the image be, and then it will be easy. You don't have to redraw it a couple of times in the board exam. So here the image is being formed very far away, and then if I bring the object within the focal point, now see what happens. There you see, first observation. Here it was real image, there it's a virtual image. That is the first observation. Second, real image was inverted. Virtual image is upright or erect. There are 2 ways in which you can call it. Erect image is the more popular word, so we'll call it by that name. So this is a virtual image, this is a erect image. And why is it a virtual image? Because the light rays are getting reflected toward the left hand side. We had to extend the rays with dotted lines and see where the rays would have met. Therefore, that is a virtual image. And of course, the third point is, this is the size of the object, this is the size of the image. So the image is enlarged. And then if we further decrease it, you see that the image is coming closer to the object. But even if you bring it very close, even then the virtual image is larger than the object. So as a summary of all this, in case of concave mirrors, can a real image be formed? Yes. Can a virtual image be formed? Yes. Can a real image be diminished? Yes. Can a real image be of the same size? Yes. Can a real image be enlarged? Yes. What about the virtual image? Can the virtual image ever be diminished than the object? No. Can it be even equal to the size of the object? No, we have dragged it so close, it can't be equal, right? All these properties that I mentioned in the last couple of lines, there are lots of questions based on that in your board exams. So this is about concave mirrors. Magnification, remember, we need to have a quantitative estimate of that. Visualization will only help you understand whether it is magnified or diminished, but in exam, you are the ones to figure out whether it is magnified or it is diminished and so on. So we'll learn the mathematics behind it. This is about concave mirror. Now let us look at convex mirror. So here is the simulation pertaining to convex mirror. First thing to observe, focal length is positive, right? And here in front of the convex mirror, the object is kept at a reasonably far off distance. Slowly we are going to bring the object towards the mirror, and at every step we will keep observing what happens to the image. Straight away the first observation is, this is the size of the object, this is the size of the image. So the image is diminished. There is a use of dotted lines, so it is a virtual image. The object is facing upwards, image is facing upwards, it has to be an erect image. Now let us bring the object closer and just observe what is happening to the image. The image continues to remain erect, continues to remain diminished, and continues to remain virtual. I am bringing it even at center of curvature. The image did not change its properties, or they were not change in properties of the image. And here you see, even if I bring it and hold it at the focal point, even then the image is still virtual, image is still diminished, and the image is still erect. Let us bring it even to a lesser distance. See, I keep on bringing it closer and closer and closer. Still the image is, having the same properties like what it had earlier. So concave mirror gave rise to certain, different kind of situations, and we had to remember all that. In case of convex mirror, it is very simple. Keep the object wherever you want. The image will be erect, the image will be virtual, and the image will be diminished. This is a very simple story of convex mirror. Concave mirror, yes, there can be a real, virtual, all those things. So we have looked at 2 mirrors. Now let us look at one lens, that is the most frequently used convex lens, and we will see how the object distance changes leads to image distance and its properties. Right. So this is the case of a convex lens, and in this convex lens, the convex lens that you see, O is called as the optic center. Remember, in case of mirrors it was P, that was pole of the mirror. So here is an object kept at a reasonable distance, and this distance, when you look at the ray diagram, you will find one more change. In mirrors we had used F and C, focal point and center of curvature. In case of lenses we don't use F and C, we use F and 2F. 2F is taken as a demarcation point. Now why is it not C? Why should it be 2F? There are two ways of finding it out. Either you can do a small amount of research on that yourself, or when we meet in the 12th class, then I'll touch upon that point. Right? Presently, just remember, it will be F and 2F. So when the object is placed beyond 2F, there is a real image, inverted image, and when compared to the size of the object, the image is diminished. Now I'll bring the object closer, and you see that the image is running away. You can see that the image is running away. When the object is placed at 2F, the image is formed at 2F. In case of concave mirror also, when the object was at C, the image was also formed at C. The object size was equal to image size, object size equal to image size. The image was inverted in concave mirror, here also the image is inverted. So there are quite a few properties which will be similar, but then of course there will be a few properties which are dissimilar also. Then let us bring the object closer. As you bring the object closer, you see that the image is running away, and you see there is a situation where the image has to be plotted even beyond the screen. This is where again I re-insist, practice your ray diagrams, otherwise this kind of a thing can happen in your exam, right? And then when you bring the object within the focal point, these rays begin to diverge. So you see the need for dotted lines, and this is where you see a virtual image. So when the object distance is less than the focal length, a virtual, erect, enlarged image is formed by a convex lens. And even if I bring the object very close, the size of the image is always larger than the size of the object. Let me move it a bit further so that you can see them clearly. This is the size of the object, this is the size of the image. So convex lens also is kind of complicated as concave mirror. Can it form a real image? Yes. Can it form a virtual image? Yes. Can the image be of a larger size? Yes. Can it be of smaller size? Yes. Can it be of equal size? Yes. I will leave the analysis of concave lens to you. Right? You can do that yourself. You can, visit the simulation, vary the parameters a little bit, and analyze for yourself as to what the nature of the image will be. The only hint I will give you is concave lens in many ways behaves similar to convex mirror. Okay, so having understood this, let us see what is this new quantity called magnification, what is the formula for magnification, how do we calculate magnification, and take up a few numericals on magnification.